problem, we have methane that's at 10 megapascals and 300 Kelvin. And it says that it's heated at constant pressure until its volume has increased by 80%. So we know if this is heated at constant pressure, we know that the volume has to increase, because if the volume didn't increase, the pressure would go up. So basically we're adding heat. So I'm going to assume that we have a piston cylinder system, because since it's at constant pressure, the volume is going to be increasing when we're heating it. And we have methane, and it tells us that P1, so the pressure, and I'm going to call this state 1, so the pressure is equal to 10 megapascals, and T1 is equal to 300 Kelvin, and then V1. And it doesn't give us a specific value for V1, so I'm just going to put V1 for now. And then at state 2, so we've added heat to this piston cylinder system, and it's increased the temperature and the volume. So I'm going to make that volume a little bit bigger. So the pressure is still the same, so P2 is equal to, I'm going to say P1, which is equal to 10 megapascals. T2 is what we're looking for, so I'm going to put a question mark. And V2 is equal to 80. So it says the volume is increased by 80%. So that means that V2 is equal to 1.8 multiplied by V1. So now it says, so we want to determine the final temperature using first the ideal gas equation of state, and second, the compressibility factor. So let's start with the ideal gas equation of state. So let's put ideal gas equation of state. And so since we have a system that's changing, we're going to want to start with this. So P1 V1 over T1 is equal to P2 V2 over T2. So right away we can see that the pressures are going to cancel out because they're the same. So P1 is equal to P2, so they're just going to cancel out. And we're left with V1 over T1 is equal to V2 over T2. So T2 is what we want, so we're going to solve this equation for T2. So T2 is equal to T1 multiplied by V2 over V1. So now we just plug in our information. So we have T2 is equal to, T1 is 300 Kelvin, and then V2 is 1.8 V1 divided by V1, so those are going to cancel, and this works out to 540 Kelvin. Okay, so we calculated that the temperature at state 2, so after the heat had been added and the volume increased, the temperature is now 540 Kelvin. Now let's calculate this using a compressibility chart. So we want to solve the same problem using a compressibility chart. So what we're going to need to do is calculate the reduced temperature and reduced volume. So for state 1, so the reduced temperature for state 1 is equal to the temperature of 1 divided by the critical temperature. And so we can look up the critical temperature and pressure. So we're going to want to look up, so we're going to want the gas constant and the critical temperature and pressure, and we're going to just look all of those up. So R, and this is for methane, is equal to 0.5182 kilopascal meter cubed kilogram Kelvin. The critical temperature is equal to 191.1 Kelvin, and the critical pressure is equal to 4.64 megapascals. The reduced temperature at state 1 is equal to 300 Kelvin, because T1 is 300 Kelvin, divided by the critical temperature, which is 191.1 Kelvin. So this is equal to 1.57. The reduced pressure is equal to P1, and this is for state 1, is equal to P1 over P critical. And this is equal to 10 megapascals over 4.64 megapascals, which is equal to 2.16. All right, so we have the reduced temperature and pressure at state 1. So what we want to do is look up Z1 and also the reduced volume on a generalized compressibility chart. So let's go to a chart. So here's our generalized compressibility chart. We calculated that the reduced temperature was 1.57 and the reduced pressure was 2.16. So this first chart is for reduced pressures between 0 and 1. So we're going to want to use this chart for intermediate pressures for reduced pressures between 0 and 7. So our reduced temperature was equal to 1.57 and our reduced pressure was equal to 2.16. So the way I'm going to use this chart is I'm going to find the reduced temperature first. And so remember, the reduced temperature is, so here's the reduced temperature. So it's these lines that are going like this. Like these are all the reduced temperature lines. And we're at 1.57, so I'm going to look for, here's 1.6. So that means that it's going to be slightly below this line, so maybe about right here, like along this line somewhere. So now what we need to do is find the reduced pressure. And so the reduced pressure is along the x-axis. So we have 2.16, so that is going to be somewhere between 2.0 and 2.5. Going to be about right here. So so then if we follow this up, we're going to find where it meets the reduced temperature line. And then what we're going to do is follow this over to the y-axis, and we're going to read off what z is. So z, I'm going to say that this is about, let's see, I'm going to say that this is the z1 is about 0.86. And we also want to get the reduced specific volume. So the lines that are going, like if we look at this chart, the lines that are going like this, these are the reduced volumes. So you can see reduced volume right here is 0.2. So let's go look at where we're at. So the reduced volume right here, like along this line, is approximately 0.6, and along this line is approximately 0.7. So it looks like we're somewhere between the specific volume of 0.6 to 0.7. We're a little bit closer to the 0.6 line, so I'm going to say that the reduced specific volume is approximately 0.63. Then what we can do, we know that the volume in the piston cylinder increases by 80% when we heat the methane. So we can say that the specific volume at state 2 is equal to 1.8 multiplied by the specific volume at state 1. And we know what this is. So we know 1.8 multiplied by and then 0.63. So this is equal to 1.134. So now we know the specific volume, or the reduced specific volume. I guess it's the pseudo-reduced volume at state 2. And we also know the reduced pressure because it's the same as the pressure at state 1. So we know that this is still 2.16. So what we can do is find the Z value, so Z2. So we can use, so we want to use, let's put this as VR2. We want to use these two values to, so we want to look up these two values on the chart to get a value for, to get our Z2 value, our compressibility factor at state 2. So what I'm going to do, I already know that 2.16 is already marked. So what I'm going to do is find where that crosses the specific volume line at 1.134. So this, looking at the specific volumes, here's 1, here's 1.2. So that means that this is going to be somewhere between the 1 and the 1.2. Is going to be closer to 1. So let's just mark this line. And then we want to go up for the from the reduced volume to this line. And then what we're going to do is go over to the y-axis and read off our our Z value. So I'm going to say from these that Z2, this looks like it's approximately 0.98. So Z2 is approximately 0.98. So we know from, and the equation is given right here, but we know that Z is equal to PV over RT. And we can specify that these are all 2, just because we're looking at state 2. And then this volume right here, this is the specific volume, but we have the pseudo reduced volume. So what we need to do is solve this pseudo reduced volume equation for the specific volume, and then we can plug that straight into this equation. So what I mean by that is, let's just write down the pseudo-reduced volume is equal to the specific volume over RT critical over P critical. And I'm going to specify that this is V2. So what we want to do is solve this equation for V2 and plug it into there. So V2 is equal to VR. And I recommend going through this math and verifying it for yourself. So VR multiplied by the gas constant multiplied by the critical temperature divided by P critical. So now plugging this into there, and so I'm going to plug this into this equation, and what I'm solving for is T2. Everything else is known. So I'm just going to say that T2 is equal to P2 multiplied by the reduced specific volume multiplied by the critical temperature divided by Z2 multiplied by the critical pressure. So this is equal to, P2 was 10 megapascals, so 10 times 10 to the third kilopascals, and I'm going to want kilopascals because our gas constant has kilopascals in its units, multiplied by the reduced specific volume, which we calculated here, so that's 1.134 multiplied by the critical temperature, which is 191.1 Kelvin, divided by Z2, we looked that up, so that was 0.98 multiplied by the critical pressure, which is 4.64 times 10 to the third kilopascals. And I guess actually we could have left these in megapascals. I forgot that we canceled out the gas constant. Okay, so the kilopascals are going to cancel, and we're left with Kelvin, which is what we want because we're looking for a temperature. So this works out to 477 Kelvin. So from the compressibility chart, we calculated that the temperature was 477. Well, let's just go to a new slide. So from the ideal gas law, we calculated that T2 was equal to 540 Kelvin. And from the compressibility factor, we calculated that T2 was equal to 477 Kelvin. So the question is, which result is more accurate? Well, let's look at a few things. First of all, there's a few things from the compressibility chart. So let's go back to the compressibility chart. If we look at the compressibility chart, like let's look at this one. If at low pressures, so in other words, PR is much less than, so the reduced pressure is much less than 1, gases behave as an ideal gas. And at high temperatures, so TR, like a high temperature would be considered, say the reduced temperature is greater than 2, we can also assume ideal gas unless the reduced pressure is much greater than 1. And then the deviation from ideal gas is greatest around the critical point. So this would be where the reduced temperature is equal to 1 and the reduced pressure is equal to 1. So for these up here, we can assume that that our gas probably behaves as an ideal gas. Here, this would be around critical point. Deviation from ideal gas is greatest. So let's look at this compressibility chart. So if we have a gas that is kind of falling in this region around here, so this is so the reduced temperature is greater than 2 unless the pressure is much greater than 1, so then we would be down on this chart. So if the reduced temperature is the reduced temperature is greater than 2, we can probably assume that it's an ideal gas. So basically, if you're in this region of the chart, it's probably a good assumption that you have an ideal gas. If you're somewhere else, like let's say you're over here, this gas is non-ideal. So like right here, this would be, here's the reduced temperature is 1, reduced pressure is 1, so we can see the deviation is pretty high. So let's look at what we have. So going back to slides. So we have at state 2 our reduced pressure. So at state 2, our reduced pressure was equal to 2.16, and so this is a pretty high pressure. So remember, at low pressures, so the reduced pressure is much less than 1, gases behave as an ideal gas. So first of all, we have a pretty high pressure, and let's look at our temperature. So we know what the temperature is now. So we know that when we first started the problem, we didn't know what our temperature was, but now we know that the temperature is 477. And if we divide that by the critical temperature, we get that this is 2.5, so this would be temperature reduced for 2, so TR2 reduced. So this is greater than 2, because remember, if the temperature reduced is greater than 2, we can assume that it's an ideal gas, unless the pressure is much greater than 1. So since the pressure is kind of high, I would probably say that this gas is that our temperature calculation is more accurate with the compressibility factor or charts, assuming that you're getting the accuracy that you need from reading the chart. With that said, if you don't need a lot of accuracy, the ideal gas law might be sufficient. It just depends on what kind of accuracy you need. But the compressibility factor is likely going to be more accurate in this case.